It's a pleasure to have Christine visiting us from the Institute for Advanced Study. She's going to tell us about Chiral Algebras and SCFTs in 40 and 60.
Thanks. And thanks for the invitation to visit to give this talk. This is going to be sort of an introductory overview to work that I've been doing for the last couple of years with a bunch of co-authors. Madalena Lemos, Pedro Leandro, and Wolfgang Pilares are students of Leonardo Rastelli at Stony Brook, and Walt Van Rees is another postdoc who's now at CERN. So as is alluded to in the title, the topic of this talk is four-dimensional theories with n=2 superconformal symmetry, and six-dimensional theories with the maximal superconformal symmetry, which is 2, 0. And the story I'm going to be telling applies to both of these two cases, but I'm probably going to end up saying more in detail about the four-dimensional case because there's just sort of a richer story, it turns out, there. Although, of course, 6 dimensions is a fun number of dimensions to be. And I'm going to be talking about these from an algebraic point of view, which is to say that the main language I'm going to use and sort of the results that I'm going to describe are in the form of statements about operator algebras in theories with this amount of supersymmetry. So for the most part, I'm not going to spend much time talking about fields and Lagrangians and path integrals. Instead, I'm going to be thinking of these theories to the extent that you can think of them as some algebra of operators, which is a good way to think about conformal field theories, because if you know about the operator product expansion between operators in these theories, essentially you know how to compute everything about correlation functions of local operators. So this is not a huge sacrifice to use this language. And just to make sure I don't miss out on the chance to deliver it, I'm going to start out with the punchline. Which is in any CFT of this type being in one of these numbers of dimensions with this amount of supersymmetry, there exists a closed subalgebra of the operator algebra. So I might call it A with a subscript chi inside of some complete algebra of local operators that is isomorphic to a two-dimensional chiral algebra. And a handful of consequences of this fact are the existence of fairly interesting 2D40 and 2D60 dictionaries that relate the properties of whatever theory I started with and some chiral algebraic properties. This fact ends up implying the existence of new unitarity bounds for the central charges of these theories. It makes it possible to compute certain three-point functions and extremal correlators in theories that otherwise I would have no idea how to compute them in. For example, the six-dimensional theories with 2, 0 supersymmetry. And there are many other consequences, some of which I may get a chance to talk about, and others of which I won't. So with that as the thesis statement, just a quick framework for how I'm going to talk about this. I'm going to start out with a fairly abstract derivation of this fact. And that's going to come in 3 parts, one of which is going to be a hopefully very fast review of chiral algebras for people who haven't been spending time with 2-dimensional CFTs recently. And then an interlude on Q cohomology, which is going to be the main algebraic trick that I use. And then the precise story of where this subalgebra comes from. Then, to make it slightly less abstract, but maybe more trivial, I'll just write down how we get this structure in the case of free theories where we already have complete control. We can at least see sort of the way the moving parts fit together. And then I'll describe more robust features of the correspondence between 4D and 6D theories of chiral algebras. So these are going to be aspects of this connection that hold, even when I know very little about my original theory. It could be some complicated non-Lagrangian theory that I don't have any useful tools for analyzing normally. And then I'll end with some discussion of sort of the catalog that started to develop for connecting superconformal theories that we might think are interesting for one reason or another, and some chiral algebra that maybe is tractable or something that we already know something about. So, the usual occurrence of chiral algebras is in the context of 2-dimensional conformal field theories. And let me remind you how this works. So in 2-dimensional conformal field theories, the symmetry group is at least SO3, 1, working in Euclidean signature. This is the conformal group in 2 dimensions, which is conventionally broken down as a holomorphic and an anti-holomorphic group of Mobius transformations, where, just to introduce the terminology, which is pretty standard, the generators of these groups are L0 plus minus 1 and L0 bar plus minus 1. So the operators in a 2D CFT line representations of this symmetry algebra, and in particular, they live in conformal families with some primary operator, and then derivatives acting on it, and anti-holomorphic derivatives acting on it, et cetera, where the relevant quantum numbers are the eigenvalues of L0 and L0 bar on the operator. So these operators live in some highest weight representations of SL2 and SL2 bar, and the relevant thing to give you is what the eigenvalues of the cartan are on the highest weight. So
The person is just with the global conformal, not with Virasoro.
So I haven't gotten to Virasoro yet because I haven't defined chiral algebra in the Virasoro symmetry as an example. But yes, right now I'm just talking about the global conformal.
So 2D people often call these quasi-primary.
Yes. So, given that this is what is automatically true representation theoretically, the thing that I can then define is the chiral algebra of the theory, which is the set of operators for which, well, L bar 0 or L bar plus minus 1 commute with the operator. So these are operators that are in the trivial representation of SL2 bar. They may not be in the trivial representation of SL2. And if that's the case, then there are a number of immediate consequences which are useful for a couple of different things. So O minus 1 bar is an anti-holomorphic derivative. So this tells me that these operators are sort of meromorphic objects. Their anti-holomorphic derivatives vanish. That tells me that the OPEs are meromorphic functions of the positions where I'm putting the operators. And it tells me that the correlation functions are meromorphic functions of the operator insertion points.
What was this bracket with 3?
Oh, sorry, this is just trying to say that it's true for all of them, L0 and plus minus 1. I apologize. I'm just,
Okay.
all the generators of that symmetry algebra commute with it.
I see, okay.
So the operator is in the trivial representation. So this is telling me that there's a subalgebra of the set of operators, which essentially acts as a meromorphic collection of objects. All of the correlation functions, all the OPEs, depends only on the depends holomorphically on the insertion point in the plane, and not anti-holomorphically. So this is one useful thing already. So normally, and I'm going to say it next, normally we sort of use this kind of a structure to then say a lot more about the full CFT. But ignoring the rest of the CFT, ignoring the operators for which this isn't true, there's already sort of a closed subsector, which is particularly tractable. In particular, once I'm talking about meromorphic functions, it's really easy to write down answers because they're just determined by their poles and residues, instead of having to worry about some complicated real analytic functions. So these are nice features for a set of operators just amongst themselves. And of course, in 2 dimensions, there's a lot more that's true. It's also the case that if I multiply an operator by any power of z, then d bar on this thing is still 0. And that means I can define infinitely many conserved currents. Or infinitely many conserved charges. And this is where I get something like the Virasoro algebra. So if this operator is a stress tensor, then the charges that I define this way are the modes of the Virasoro algebra. If the operator that I define this way is something like a conserved current, which is of dimension 1, then the things that I get this way generate some affine current algebra, or an affine Lie algebra. And then there are all sorts of more complicated things that we may see later in the talk. But the 2 classic examples are Virasoro and affine Lie algebras. So this structure is usually used to then motivate the idea that we can say a lot more about 2-dimensional CFTs than non-2-dimensional CFTs, because we have infinite dimensional symmetry algebras. And for example, you can end up with theories that have finitely many representations of the infinite dimensional symmetry algebra, and that gives you so-called rational CFTs. This feature of being able to organize other operators into representations of some much larger symmetry algebra is not going to play that much of a role in what I'm talking about in the rest of the talk. I want to emphasize that really already just the statement that there's a collection of operators that have very simple meromorphic correlation functions is a nice property. And if you know that much about a set of operators, then you can make a lot of progress on trying to solve the associativity conditions for the algebra, because meromorphic functions are nice. So that was a lightning review of this structure that exists naturally in 2 dimensions. So what happens in more than 2 dimensions? My claim is that I'm going to end up with some structure that looks like this, even when I'm not in 2 dimensions. So, is this line here because I'm not supposed to write to the right of it?
Yes. Because it's
Where that's-
recorded.
Where
It's
that screen is, that's pretty much
But I think the camera
Okay.
can't see.
The camera cannot see.
the already.
Yeah.
Okay, I won't go to the right of it. So, in more than 3 dimensions, or in more than 2 dimensions, 3 or more dimensions, by conformal symmetry is still SOD plus 1 comma 1. Now this doesn't factorize into something like SL2 times SL2 bar, it's just some simple the algebra. The operators in my CFT are still some things that transform in irreducible representations of this. So there's some operators labeled by a scaling dimension and a spin, and then I have their derivatives, which are conformal descendants. And if I don't already know why it won't work, I could just imagine that I'm going to do something really stupid and get that chiral algebra story again. I could say, oh, well, inside of SOD plus 1 comma 1, there's an SO3 comma 1 subalgebra. I can just isolate the part of the conformal algebra that acts on a plane, like 2-dimensional Mobius transformations. So I could take SL2 times SL2 bar inside of this, and accordingly, the operators that were in some irreducible representations of SOD comma D plus 1 comma 1 will decompose into some infinite linear combination of representations of SL2 times SL2 bar. And I can
finite dimensional, usual finite dimensional representations.
these are infinite dimensional representations because the relevant real form is really the SL2 form, not like
So
SO2.
So they're low switch reps and
Yeah.
build up on them.
Yeah. This
Okay.
is, I mean, these representations will still look like these representations, where I have some quasi-primary operator, which is annihilated by the L pluses, and I can act with all the L minuses.
Okay.
However, the thing that one immediately discovers, and is probably intuitively true, even if you haven't tried to work out the group theory, is that if you start out with an irrep of SOD plus 1 comma 1, and you decompose this way under SL2 times SL2 bar, you won't get anything that's in one of these chiral representations. You won't get anything with HI bar equals 0 and HI not equal to 0. So that's a relatively elementary consequence of the fact that this group doesn't factorize into these 2 different simple parts. It's simple on its own. Okay, so that's really no surprise because we probably all already know that CFTs in more than 2 dimensions are less nice than CFTs in 2 dimensions. So doing the stupidest possible thing won't work. But what I really have in mind to work on here is superconformal field theories, and so I should be using supersymmetry for something. And there's a way to get past this stupid problem using a familiar trick from supersymmetric quantum field theory in a way which is maybe slightly unfamiliar.
So if you do the stupid thing, is there like some general statement you can make about how HI and HI bar are correlated? Like you say that I can't have 1, 0, and 1, 0 for any representation of this decomposition, right?
Yeah. So
do
the
they have to be
HIs
the same?
Sorry?
Do they have to be the same then? Each?
No, so with respect to the rotation generator in the plane, H is something like delta plus L over 2, and H bar equals delta minus L over 2. So L is the rotation generator in the plane,
Okay,
and delta is the scaling dimension.
okay.
So the thing I want to do is find some way of tricking my operators into thinking that they transform in the trivial representation of this anti-holomorphic SL2 that acts on the plane, when actually they don't. And there's a slightly familiar story from sort of run-of-the-mill supersymmetric quantum field theory for how to do this. So in order to motivate that, let me just do a 4-line reminder of a fact from 4-dimensional n=1 supersymmetry. So in 4 dimensions, if I have n=1 supersymmetry, then I have supercharges which transform in right-handed and left-handed spinor representations of the rotation group, and their anticommutator is the momentum generator in 4 dimensions. I can also have operators called, confusingly, chiral operators, and this now does not have to do with chiral algebras, but there are chiral operators, which are operators which commute with both helicities of one of the supercharges. Now, if this is the case, then using the Jacobi identity, I can prove that the derivative acting on that operator is Q of something. In particular, it's Q, or Q tilde of the operator. This means that if I now work in Q cohomology, meaning that I identify an operator with an operator plus Q of anything, then this derivative, where now I've used a notation where I've put O in square brackets and put a Q as a subscript. But that means I'm working at the level of this equivalence relation. Then this becomes 0. So this means that to the extent that I am allowed to work at the level of this equivalence relation, then I've changed this operator OI from an operator that transforms in the usual representation of the translation group, the operator that if I act with the translation generator, it moves a little bit, into sort of an effective operator which transforms in the trivial representation of the translation group. So this is the trick. And hopefully, after having said this, after I said the thing I said before, it becomes clear what the trick is going to be for getting chiral algebras. I now know that what I should be looking to do is to work at the level of the cohomology with respect to some supercharge, so that at the level of that cohomology, the operators now live in a different representation of the SL2 bar algebra. And so I can get something which is invariant. So let me write that down. What is the strategy? So, what I was already implicitly doing, I'm going to fix some plane inside of d-dimensional space. That's a plane on which SL2 times SL2 bar act. And now I'll find a supercharge, which I will denote by a funny Q, because I'm not sure what it's going to look like at the end of the day, with a certain number of properties. I want Q to square to 0. So it's a nilpotent operator on the Hilbert space of my theory. That means that it makes sense to work at the level of cohomology. This can actually be relaxed in principle, but I'm not going to have to. I also want it to be the case that this supercharge that I haven't defined yet commutes with any of the generators of the holomorphic SL2. This is because once I'm operating at the level of the cohomology of this supercharge, I want the action of the holomorphic SL2 to still be well defined. Now, the key part that mimics what happened in the chiral ring story in 4-dimensional n=1 theories is that I want Q commuting with something to give me SL2 bar. If I can get this, if I can define this supercharge, then at an abstract algebraic level, I'm done. It will then be guaranteed that once I pass to the cohomology of this supercharge, I will just have reproduced exactly the setup that I had in 2 dimensions. Only now, instead of being in honest 2-dimensional space, I've just restricted by hand to live on this plane where I effectively have 2-dimensional conformal symmetry.
Question. Are those brackets being done at the Q cohomology level?
These brackets?
Yeah.
No, these brackets are true are supposed to be true on the nose. So this third condition can also be relaxed, and in fact has to be relaxed, because what I wrote is not possible. I need a slightly modified version. So you can go and check, you can go and look up all of the superconformal algebras in an arbitrary number of dimensions, and just try to figure out whether you can write down a supercharge like this that will obey these conditions, and you will fail. But there's a slightly relaxed version that you can succeed at, which is to have a twisted SL2 bar, which is the diagonal subgroup or the diagonal subalgebra of that antiholomorphic SL2 and an R symmetry. If I'm being very precise, it's a complexification of an R symmetry. So this turns out to be possible. It's not trivial. In fact, for most superconformal algebras, if you go back to your list, you won't be able to do it. Instead, you find this supercharge precisely when there's an SU1, 1/2 subalgebra of your superconformal algebra. And again, you can go back to your list and figure out when that's true. And there is such a subalgebra in SU2, 2/2. That's the superconformal algebra of 4-dimensional n=2 theories. There is such a subalgebra of OSP 8/4. That's the superconformal algebra of the 2-0 theories in 6 dimensions. And so that covers the 2 cases that I'm talking about in this talk. There's a more obvious fact, which is that SU1, 1/2 is a non-proper subalgebra of SU1, 1/2, which means that in 2-dimensional theories with 0, 4 supersymmetry, you can play all the algebraic tricks that I'm talking about. I'm not going to talk about it anymore. Somehow, it's a little bit anticlimactic to rediscover chiral algebras in 2 dimensions when we already had them. Nevertheless, it is the case that the chiral algebra that you define using this cohomological construction in 2-dimensional 0-4 theories is different than the chiral algebras that naturally occurred in sort of the original way. So it's still an interesting topic. And now, I can admit to what this square Q looks like. In all cases, it takes the form of a Poincare supercharge plus a superconformal charge. So this makes it abundantly clear that it was important all this time that I've been working with superconformal field theories. I couldn't have gotten away with sort of generating something that looked like 2-dimensional conformal invariance in a non-conformal theory in 4 or 6 dimensions. And if anyone really cares, which I'm sure they don't, in the 4D case, which is the case where I've memorized it, it takes this form using some standard conventions. But it really doesn't matter. The thing that should probably matter is that this is something that looks like Q plus S.
I supposed to put in for the dot?
Anything.
Anything?
So, well, sorry, anything that's a symmetry of your theory. So all of this supercharge finding is happening at the level of the superconformal algebra of your theory.
Okay.
So so the things that appear in dots are symmetries of the Hilbert space of your theory. So in practice, in order to get the various raising and lowering and Cartan generators of the sky, when I put it for this dot, are certain appropriately chosen Q's and S's and linear combinations of those.
If you didn't choose the Q's and S's appropriately, you would get something else that's not.
That's right. So, at some extremely formal algebraic level, this establishes the claim. This means that it's guaranteed just by the rules of symmetry, that if I start playing around with local operators, which define non-trivial cohomology classes of this Q, so things that are annihilated by that Q but are not that Q of something, then those operators will act like they are invariant under a twisted version of the SL2 bar. They will be acted upon well by the SL2. And so all of the rules that allows me to get chiral algebras in an ordinary two-dimensional CFT will apply.
And those are going to form a subalgebra because Q acts like a derivation.
That's right. There's one small loophole that could still exist, which will now be closed, which is that you could imagine that there are actually no operators that are in the Q cohomology. So, an important question is, what operators are involved? And the answer naturally sort of has there's sort of a two-step answer. You could answer it all at once if you want it, but the easiest question to answer is if I put an operator at the origin. Note that because Q has a Q and an S in it, there's really sort of a privileged notion of the origin, because Q's and S's are related by Hermitian conjugation in radial quantization relative to a particular origin. So there's a well-defined notion of the origin. And for an operator at the origin to define a non-trivial Q cohomology class, it simply has to obey a certain relation on its quantum numbers. What do I call it? Delta. So this says that the scaling dimension of the operator minus its eigenvalue under rotations in this plane that I've picked out, divided by 2, is equal to its charge under the Cartan of this R symmetry that I twisted by. I suppose I should mention, in the 4-dimensional n equals 2 case, it's clear that this is the complexification of the usual SU2 R symmetry. In the 6-dimensional 2, 0 case, there's an SO5 R symmetry, and the thing that appears here is the vector SO3 inside of SO5. So the thing I get by taking 3x3 matrices inside of 5x5 matrices for SO5. And so it's the Cartan of that particular SO3 subalgebra that appears here. And if you go and refer to some text that classifies representations of superconformal algebras, you'll find that there are many interesting operators that obey these conditions. I won't go into it in detail. It includes a lot of half BPS things. It includes a lot of quarter BPS things. It also includes lots of exotic things that transform in so-called semi-short representations of the superconformal algebra that you only encounter if you've ever really embraced superconformal representation theory. I'll say a little bit more in a moment in the simple cases of free theories about what sorts of operators these are. But this is only at the origin. So Q has an S in it, and S doesn't commute with translation. So if I translate this operator in the ordinary way, then it will no longer be annihilated by Q. But I already know how to fix that because I know that sort of the right version of the anti-holomorphic symmetry algebra on the plane is this twisted guy. So if I want to move the operator away from the origin and still have it be well defined at the level of cohomology, I need to define sort of a twisted O at a point Z, which I translate in the usual way in the plane, except that I have these hatted generators instead of the barred generators. If these guys were barred, this would be the ordinary way that I translate operators. Because they're hatted, these hats include lowering operators in the SL2R symmetry. So what this is telling me is that if I had my operator at the origin and it transforms in some representation of SU2R, then as I move it around, I have to pick out a different component of its SU2R representation depending on what point I'm putting it at in the plane. And I can be a little bit more concrete. What this ends up looking like so if my operator transforms in the spin k/2 representation of this SU2R, then I get the highest weight state of that representation, plus z bar times the next times once acting with the lowering operator, plus z bar squared times twice, etc., up until z bar to the k times acting with the lowering operator. So this is a weird operator to be using. This gives me some funny slice in the space of operators in my theory, which depends in a specific way on what point in the plane I'm inserting my operator at. But it's only these guys that are going to be well defined at the level of Q cohomology. And so it's only by studying correlation functions of these particular spatially dependent guys that I'm going to get the structure of a Chiral algebra.
Well, what does it mean physically? An operator depending on the
It's just
position on the
It's just
plane?
an instruction of which operators I should choose to study. So for any particular values of z bar, these are just numbers, right? So if you tell me that you want to look at the plane and you want sort of this configuration of operators, then there are some particular values of z bar at those 3 points. And this is an instruction
So
that
Z is not a coordinate on the world sheet of string theory or something like that, then, is it?
z is a coordinate on a plane.
It's an auxiliary plane or what?
No, it's a real plane. It's a plane, it's the
Where is it sitting?
it's the plane that I've picked out by hand inside of d-dimensional space.
Oh, in the d-dimensional CFT?
Yeah.
Conformal field theory.
So d was 4 or 6.
I see. Okay.
Just to throw some extra words out, another way to say what's happening, just if you prefer the language of background fields, is that what I've done that's led me to move operators around like this and include these spatially dependent pieces, is that I've turned on a background gauge field for the SU2R symmetry, which is lower triangular. I can do that, I can couple my theory to that background gauge field, and then parallel transport with respect to that background gauge field will precisely tell me to do this. Okay.
So these are covariantly constant sections. If I look at that gauge field is defining, so that's U2R.
Yeah, yeah, exactly. Okay, so I'm finally going to say a couple things about specific theories. They're going to be the most boring theories because they're free. But it still shows you, it will still show why sort of this precise prescription involving putting in factors of z bar does the thing I want, which is to end up with some meromorphic structure. So what's the simplest free theory? well, the simplest free theory in 4 dimensions with n equals 2 superconformal symmetry, I would say, is the theory of free hypermultiplets. So this is some collection of free scalars and free fermions. And if I stare at my fields and remind myself of what their quantum numbers are, then I find out that the complex scalars q and q tilde have dimension 1, spin 0, and R symmetry charge 1/2. So they obey this condition. Now they live in doublets of SU2R symmetry. They look like this. So it's the top components which obey that condition, and therefore if I put the operator at the origin, I'm taking the top component. But if I put the operator in an arbitrary position, then I get these particular combinations. And just for the sake of notation, what I have in mind is thinking of these up to Q exact things. Although I'm free to just use these representatives themselves. And now I can do something simple, like take the 2-point function of these two things. Or I can look at their OPE. It's a free theory, so I know what the OPE is. And I find, if I take the OP of this guy put at Z, and this guy put at W, well, I get a denominator of the distance squared. That's what I normally get from free scalar OPEs in 4 dimensions. But from this Z bar, this guy becomes a W bar. If you just work out the algebra, you get a Z bar minus W bar on top. And so you magically get something which is meromorphic. You can quote unquote work out the rest of the theory. So it's a free theory, so I know all the operators in the theory and I know all of their quantum numbers. And all of the operators in the theory that obey that condition are words that I can make out of Q and Q tilde and their holomorphic derivatives in the plane. So once I translate that into this language, what I'm saying is that I have a chiral algebra, or a meromorphic operator algebra, which has these fields Q and Q tilde and their holomorphic derivatives. And that's it. And they have this OPE. And that's a well-known chiral algebra once I tell you that you should call this beta and this gamma. This is a beta-gamma system of dimension 1/2, 1/2. You can do the same thing with free vector multiplets. I'm not going to write it down because it takes time to write things down.
Just
But-
before you go on, is
Yeah.
this not potentially a infinite dimensional higher spin algebra in 7 dimensions? In a asymptotically ADS7 space-time. This is a 6-dimensional free CFT basically we are talking about, aren't we?
In this case, I started out with a 4-dimensional theory. So
Well, the
these are just free
hyperdrive 4, I
hypermultiplets.
see. Can you lift it to?
You can do the free tensor multiplet in 6 dimensions if you want. I can tell you the result, although I won't write out
Okay,
all the
I'm
equations.
sorry I
here.
missed your point about 4D.
No, it's
Then
fine.
I would repeat my question by replacing ADS7 with ADS5. A higher spin algebra in 5 dimension, I would consider as a candidate to holographic dual, anti-dual to this. Have you considered that aspect of this problem?
We've thought a little bit about the holographic dual. I prefer to think about the holographic dual once I've gone to a theory where I already know the holographic dual, and then I can just try to do this story.
Well, there's
So by
an
starting with
existing
something like n equals
algebra and linearized field equations already known in 5D. There's a candidate for the higher spin theory, spectrum, symmetry, but linearized.
I mean, this is a really boring theory.
Not so boring in the bulk, 5-dimensional bulk. Anyway, we can discuss later.
We can discuss that. I
Okay.
think there's an interesting question about how to tell the story in the bulk, but it's not completely trivial, because in order to end up with this construction that looks this way, I've had to do a bunch of funny things by hand. I've had to restrict my attention to operators that are inserted on a plane. I'm not allowed to insert them at other points away from that R2 subspace. And I've also had to do this funny twisting where I take these linear combinations. So it's interesting to ask in a holographic dual, what does that whole prescription look like? And what language would I use in the bulk to sort of do this simplification?
Perhaps topological field theory of sorts.
It's some sort of topological, well, not quite topological, but holomorphic twist. So just to report so this is an example of a general result, which is that free theories have free chiral algebras, where free chiral algebra means that the OPEs of the generators don't have any fields appearing in the singular terms, just constant terms. And that means that in order to evaluate correlation functions, I can just do weight contractions. So this turns out to also be true for the 4D free vector. In that case, the operators that obey this condition on their quantum numbers are the positive helicities of the gauge genomes, which are in the highest weight state of their SU2R representation. And after I go through the whole song and dance and write down the OPEs, then again, with some clever renaming, I end up naming the operator that comes from this, B, and I end up renaming the operator that comes from this, partial C, and I end up with a BC ghost system at dimension 1, 0. And just to be pedantic, because I named lambda DC, I don't have the C0 mode itself, and there's a consistent truncation of the BC ghost system where you throw away the C0 mode that was exploited by Friedan, Schenker, and Martinek long ago, and it's sometimes called the small algebra. But it's a consistent thing to throw away that 0 mode. And then I can do the 6-dimensional free tensor.
What about higher tensors? Can you go beyond, in 4D, I can think of the hypermultiplet, vector multiplet as special representation of the
Of the superconformal.
of ADS5 again, going back to ADS5 picture. Those are called doubleton representations in the group theory power. But you can have higher spin versions of them. Those are short representations of the ADS group, ADS5 group. Now, you can go beyond vectors, I think. You can have a higher spin version of these things. So in other words, I'm asking you whether you can have a CFT in 4 dimension with fields that carry spin beyond 1. That's my question. Is that a possibility in your scheme?
So I don't know, just independent of this set of constructions, I don't know the answer to your question.
But you stop at vector, right?
I stopped as vector
Okay.
because really these free theories for me are just to gain some intuition. And my plan is to understand interacting theories. And I don't think that there are interacting theories with higher spin fields.
Well, Slev might disagree with you. Maybe, I don't know. Just be.
These theories live in flat space.
Okay.
But I mean,
I would not stop at the
anything that's
vector.
allowed, anything
As a
that's
research
allowed by
project.
superconformal
Yeah.
algebra
Exactly.
has to have a story associated to it.
Right. So why stop at the vector? Do you go on?
You stop because you have other things to do.
All right.
The 6-dimensional, in the 6-dimensional free tensor multiplet, it is the free tensor it's the scalar field which obeys the rules on its quantum numbers. So you have some scalar field which is in the vector of SO5. And this ends up giving you a U1 affine current, which is a free chiral algebra. For groups other than U1, affine current algebras are not free, but the U1 case is just saying that J goes like 1 over Z squared. So that's the story of free fields. I have very little time left, so let me report a handful of facts that I hope if anyone is curious about will ask me about afterwards. So once I go beyond free theories, I can't do everything concretely by hand anymore. So in free theories, I was able to deduce these results just by actually writing down all the operators and knowing their OPEs and taking the appropriate linear combinations and doing the algebra. If you hand me something like the 2, 0 theory or some interacting n equals 2 theory, I can't do that all by hand. And so in general, I'm going to need to work hard to try to figure out how to describe the chiral algebra. But there are some universal results which follow from certain operators whose OPEs I do know by symmetry. So in particular, in both 4 and 6 dimensions, I know that I have a stress tensor operator. And the OPE of the stress tensor with itself is partially fixed by conformal symmetry, by conformal word identities. Now the stress tensor doesn't obey the condition that I erased for its quantum numbers. But in both the 4-dimensional and the 6-dimensional cases, there's another operator in the stress tensor multiplet that does obey those conditions. In both cases, using superconformal word identities, I can fix the OPE of that other operator with itself, enough to figure out what its chiral algebra counterpart looks like. And in both cases, sort of the operator in the stress tensor multiplet gives me a Virasoro stress tensor in 2 dimensions. So it gives me an operator in the chiral algebra which obeys where there's an interesting answer to what this number is. So in the 4-dimensional case, C2D, so the C that appears in this chiral algebra OPE is equal to minus 12 times the C central charge of the 4-dimensional theory. So in particular, it will always be negative because I'm starting out with a unitary CFT in 4 dimensions for which C40 is positive. In the 6-dimensional case, they're just equal. And these are facts that it turns out you could go back and check in these free cases if you had thought to ask what happened if I tried to build a stress tensor in the BC ghost system or the beta gamma system and ask what its central charge is. There's a similar story with global symmetries. So if I have global symmetries in a 4-dimensional theory, then there's an operator, which is the conserved current, J mu associated to that. And I know things about the OPE of J mu with itself because they're fixed by global symmetry. They're fixed by the word identity associated with the global symmetry. Again, J mu itself doesn't obey the right conditions on its quantum numbers to be involved in the chiral algebra, but it lives in a supermultiplet that does. And perhaps unsurprisingly, once you believe everything will work out in the nicest possible way, that other operator in the supermultiplet ends up having OPEs of an affine current algebra. So again, we see that sort of the relevant symmetry of the parent theory is reproduced in the more powerful sort of chiral algebra context after going through some song and dance where you have to find another operator in the same supermultiplet and then work out its OP using conformal word identities. And finally, I won't even write it down, but there's a last example, which is that if you start out with a four-dimensional n equals 4 theory, if you think of a four-dimensional n equals 4 theory as an n equals 2 theory, you have some extra supercurrents around, which are the generators of the extra supersymmetries. And then there's a similar story you can play with those operators, and you end up getting, sure enough, supercurrents in the 2D chiral algebra. So this gives you some general starting points for understanding the chiral algebra of an interacting theory. There are just basic things that you might know. Like in the 2-0 theory, we know it's central charge. In a bunch of four-dimensional n equals 2 theories, even ones without Lagrangians, like these Minahan-Tomaszewski theories or something, we think we know something about what their global symmetry is and what their central charge is. And so you get some starting point in terms of, well, the chiral algebra, whatever it is, has to include an affine current subalgebra with some appropriate level. I should have said K2D minus 1/2 times what people call the central charge of the 4D current algebra. Again, K4D will always be positive, so the level of these affine current algebras is always negative.
May I ask a question about symmetry?
Yeah.
A couple of years ago, some Pleben, Wimmer, and myself, we constructed at the classical level interaction of non-abelian Young-Mills theory to tensor multiplets that carry the representation of the Young-Mills group in 1,0 theory, not 2,0, 1,0. So it's interacting theory of Young-Mills to tensor. Well, it's a classical field theory construction. My question is, are you familiar with any such system that actually makes sense at the quantum level and whether it fits into your overall global scenario picture? Are you familiar with such interactions?
I'm not familiar with any such system that makes sense at the quantum level.
Or you mean you're familiar with those who have failed to make sense? Have there been attempts? Are you familiar with attempts?
Yes. Well, I don't know what level of familiarity you're hoping for.
Right.
But I am vaguely familiar with attempts to write down classical interacting field theories that have something to do with the 2,0 theory. Although, in all honesty, I don't know exactly what they're supposed to have to do with the 2,0 theory.
And your 1,0 story you may be familiar with? 1,0, Young-Mills plus tensor coupling. 1,0 in 6D.
Sorry, what is the
6 dimensions.
What is the question?
Is there any attempt to make sense of such couplings as a quantum theory, as a quantum consistent CFT?
If there are, they haven't reached me.
Okay.
Unfortunately, theories with 1,0 supersymmetry are not a part of this structure that I'm describing.
Why?
Because the 6-dimensional 1,0 superconformal algebra does not have a SU 1,1/2 subalgebra. And so I can't find a supercharge of the type that I'm using in order to define this structure cohomologically. It's just an annoyance of the superconformal algebra. It doesn't have a Q that obeys the right properties.
That's interesting.
So, I'm basically out of time. Let me abuse your hospitality just a little bit and just even more, or with even less detail, describe some interacting cases where we either think or know that we know what the complete chiral algebra is. So what the maximum structure of these interacting operators looks like. Probably the best place to start is with the 2-0 theory. So these guys are labeled by a simply laced Incan diagram, G. And the chiral algebra that I get, perhaps unsurprisingly, if you just wanted to guess something, is the so-called W algebra of type G. This is the same W algebra that appears in the HET correspondence, although you would be surprised at how hard it is to relate the construction I'm describing to the HET correspondence. With central charge equal to 4 times the dimension times the dual Coxeter number plus the rank. If you care about the connection with the HET correspondence, or the superficial connection with the HET correspondence, this is the central charge that appears when epsilon 1 is equal to minus epsilon 2, or equal to plus epsilon 2, whatever the symmetric value is that's allowed. There's a collection of sort of quasi-famous n equals 2 fixed points due to Minahan and Nemeshansky. They have E6, E7, and E8 global symmetry. There's actually more than one of them. These are the minimal ones, the so-called rank 1 theories. For these guys, the chiral algebra appears to be simply an affine Lie algebra for the corresponding global symmetry at a particular negative integer value of the level. And it turns out that there's all sorts of interesting structure in chiral algebras with these negative integer levels, and those end up reflecting for you what the chiral ring relations of those 4-dimensional theories are. So there's a lot of physics which is packaged automatically into these chiral algebras. There's a minimal Argyres-Douglas theory, which is the thing that appears at a point on the Coulomb branch of, I believe, the SU3 theory, with n equals 6, or maybe the pure SU3 theory. It's something sometimes called the H0 theory. This is a theory with no flavor symmetry. And the chiral algebra appears to be just the Virasoro algebra at a very suggestive level of the central charge. Minus 22/5 is the central charge of the non-unitary minimal model. It's called the Lie-Yang model. It's a non-unitary minimal model with a single primary that's not the identity. And I don't know what that non-unitary minimal model has to do with the Argyres-Douglas theory, but it has the same chiral algebra. And finally, let me just remark, without describing the construction, that any n equals 2 superconformal gauge theory. So any superconformal field theory that you get by starting out with a Lagrangian, of starting out with free theories and then introducing interactions in Lagrangian. For any SCFT of this type, then there's a BRST construction of the chiral algebra, where you start out with the chiral algebras associated to the free theories. So you start out with a bunch of BC ghosts and a bunch of beta gamma systems, and then you impose a certain BRST constraint that effectively takes into account the result of gauging. So this means that for any theory like n equals 4 super Yang-Mills, or any superconformal quiver, circular or linear, you have a construction of exactly what the chiral algebra is. And I think that I'm probably too far over time. So let me conclude and just mention that aside from the sort of mathematical physics side of this whole story, which has been the focus of this talk, because That's what comes up when you're just trying to get into it. There end up being a lot of applications, what seems like a lot of applications, in terms of extracting out information which is not special to this particular structure. So it's nice to have this 2D40 and 2D60 dictionary. This is a neat structure that lives inside of these superconformal field theories. But at the end of the day, the fact that these chiral algebras are very tractable and that you can understand them fairly concretely, understand what their operator product algebras look like, and even solve the associativity constraints for them, allows you to do things like figure out what the 3-point functions or extremal correlators of half BPS operators are in theories that have no Lagrangian. So getting something like the 3-point functions of half BPS operators in the 2,0 theory is something that, as far as I know, there's no way to do aside from the large N limit. In the large N limit, there's a hard supergravity calculation that Bastianelli and Zucchini did in order to read it off. But to go beyond the leading order 1/n correction, you need to be able to do quantum corrections in M theory. Here you can do it to the extent that you can understand these Wn chiral algebras. So we did this in the large N limit of these W algebras. We reproduced the Bastianelli-Zucchini result. You end up having to be able to do some annoying manipulations with W infinity algebras, but you can reproduce the answer. But in contrast to gravity, where you think that the easy thing to do is to start at large N and then get corrections in 1/n, the easiest thing to do here is to start out with like the n equals 2 or 3 case. That's much easier. And you can just read off the BPS 3-point functions on the nose. And you're essentially doing it by using crossing symmetry. You're doing it by demanding associativity of the OPE in this chiral algebra. And I don't think that you would be able to do that otherwise. So I guess with that, I am finished. So thanks for listening.
Any other quick questions for Chris?
Unitarity bounds, can you quickly say how they are doing?
Oh, yeah. I'd love to. So the issue, sort of the origin of the unitarity bounds is that once you know the chiral algebra, or even not the whole chiral algebra, but once you know certain correlators of the chiral algebra, you can read off 3-point functions you can read off certain 3-point functions of the non-chiral theory. But those 3-point functions are not guaranteed to be compatible with unitarity. So for example, the 4-point function of affine currents in a chiral algebra is completely fixed just by associativity. I won't write it down, but once I give you what the flavor group is and what the level is, then you can write down exactly this 4-point function. But then you can take this 4-point function and do a conformal block expansion in the chiral algebra language. And you get a bunch of coefficients in front of the conformal blocks, which are related to the coefficients of BPS operators appearing in, so this is a chiral algebra correlator. But there's a related correlator where instead of having used these J's, which are these funny Z-bar dependent linear combinations of operators, instead I used just the honest-to-God 4-dimensional operator. So in this case, these J's were related to half BPS chiral operators in the 4D theory. So this is some big complicated 4-point function, which is not meromorphic and is not determined by supersymmetry. But this also admits a conformal block expansion, and certain coefficients in this conformal block expansion have to match certain coefficients in this conformal block expansion. But whereas the coefficients appearing here have to manifestly be consistent with unitarity. So in particular, a C U O squared, the square of a 3-point function, has to be positive in order for this to be a unitary correlation function. In this case, that's not necessarily true. In particular, all of these chiral algebras are non-unitary in the 4-dimensional case, like I described, because they have negative central charge and negative level. So if you fix K2D and C, or let's say K4D and C4D, if you choose these wrong, then when you try to take the information in the chiral algebra correlator and read it back into 3-point function squareds of the non-chiral correlator, you'll get negative numbers, which are inconsistent with unitarity. And you can get a bunch of different relations by studying different 3-point functions. So for example, you find out that in complete generality, this equation has to be obeyed for a choice of central charge and choice of level. This comes from focusing on the singlet channel in this operator product expansion. And then you actually get a lot more relations coming from projecting onto different representations in the operator product expansion. And when these unitarity bounds are saturated, it implies that you actually have to have certain operator relations in the original theory. So when this guy is equal, then there has to be a certain chiral ring relation in the chiral ring of the 4D theory. And similarly, for a bunch of other relations that I won't write down, you get some bound where some function of k and c has to be, or there has to be some inequality of functions of k and c. And when it's equal, then it implies a certain chiral ring relation has to hold.
Any other questions? Let's thank Chris again.